we were looking at the problem less than or equal to 3 VC. Okay. So this problem, the input is a graph G such that delta G, which is the maximum vertex degree, is at most 3 and the positive integer k. The question we ask is, does G have a vertex cover of size k? Our objective was to prove that this is NP complete. It's easy to see that this problem is in NC. The proof is very similar for the as for the vertex cover. Okay. The fact that delta G is less than or equal to 3 does not change anything. Okay, so now we need to prove that if there is a polynomial time algorithm for less than or equal to 3 VC, there is one for everything in NP. We've seen that it suffices to prove that if there is a polynomial time algorithm for less than or equal to 3 VC, there is one for VC, and that's what we were doing. Okay. The trick was this. So we are given an algorithm for 3 VC. Okay, so we are given an algorithm for less than or equal to 3 VC. So we want to construct one for VC. So we take the input graph, let's say G. Okay. Now this could have vertices of varying degrees, especially vertices with degree greater than 3. Okay. If the vertex degrees are less than or equal to 3, we have no problem. Now, what do we do for these large vertices with large degree? We use the split operation. Okay. So supposing I have a vertex with large degree. Okay. What you do is you sort of split this vertex into 3 parts. Okay. Now, some of the neighbors are attached here and some of the neighbors are attached there. Okay. Essentially this is broken up into 2 parts. Some of them are attached here and some of them are attached here. Now we saw that if this has a vertex cover of size, let's say L, this has a vertex cover of size less than or equal to L plus 1. Okay. And if this has a vertex cover of size P, then this has a vertex cover of size less than or equal to P minus 1. Okay. So this is the effect of splitting a vertex into these 2 parts. Okay. So the vertex cover goes up by only 1 while we have reduced the degree of this vertex. Okay. So the algorithm is as follows. So you take G and then keep splitting vertices as long as there are vertices with degree at least 4. So G1, G2 and so on. So maybe I'll do this L times. Okay, this is done L times. So, and in GL, I know that there is no vertex with degree greater than 3. So now GL is fed into this algorithm for 3 VC. Okay, so this is now input to an algorithm for 3 VC. Okay, and the K, so initially I had a K here, right? So now I feed in K plus L, and if it says yes, then I output yes. If it says no, then I output no. Okay, this is the entire algorithm. So I take G, I want to find out whether it has a vertex cover of size K. I do this sort of transformation, I get the final graph GL. I feed this into 3 VC with my new K as K plus L. If it says yes, I say yes. If it says no, I say no. Okay. Now, if this runs in polynomial time, I want to show that this entire thing runs in polynomial time. Okay. The first thing is that there should not be too many of these steps, right? If there are a large number of these steps, the overall algorithm may not be polynomial, may not run in polynomial time. So let's first bound L. Okay. So how many times can a vertex be split into 2 parts? Okay. So supposing I have a vertex with so let's see this. So how many times can a vertex be split? Okay, this is a question we want to answer. So supposing I have a vertex with degree d. Okay, so I could split this once, twice. I mean, how many times do we do this? Well, note that each time the maximum degree will keep decreasing, okay, by at least one, in fact by 2, right. So the maximum number of times I am going to do this is d by 2, right. You can do it in fact better by splitting it in half, etc., etc. Okay. So the maximum times you will do this is actually d by 2. Okay, I hope this argument is clear. Let me repeat this. So each time I split, right, the maximum. So if I just look at these graphs, the degree of this, this vertex now is at least is at most d minus 2, right? And the next time I split, one of those vertices again I'll decrease by 2, right? And so the maximum number of times I do this is d by 2. The other way to see it is this. So let's say I have 1, 2 up to d. Okay. The first time I split it like this, I have 1, 2, and the rest. Okay, 3 on up to d. And now for this vertex, I again split it into 2 parts. So this portion remains as it is. So this portion now I split as let's say, so this is 3, 4, and then everything up to d, so on. And you can see that this is done at most d by 2 times. Okay. So the number of times the vertex of degree d is split is d by 2. So the total number of times a split occurs, is summation over all vertices, okay, dv by 2, and that we know is nothing but number of edges in the graph, right. So this half comes out, and sum of the degree of vertices is twice the number of edges, right. So the total number of times a split occurs is at most m. If the vertex has degree 3, of course it doesn't split. Okay, so here let's go back to this. I know that L is at most m. Okay, and each time you split, you add 2 new vertices to the graph. So the size of GL, V of GL, okay, is less than equal to size of V of G, and each time you split, you add 2 new vertices plus, okay, twice L. So it's at most n plus twice m. Okay, the degree of each vertex in GL is 3, so the number of edges is also some constant times n plus 2m. So the size of GL, which is the number of edges in GL, is polynomial in the size of G. Okay, it's not too big. You do not do this too many times, and the final graph that results, the size of that graph is not too big. So any running time which is polynomial in that size is also running time is polynomial in the input size. Okay, so this thing runs in time. So this, if you look at 3VC, this runs in time which is polynomial in this input, in size of GL, but that is also polynomial in size of G. Okay, so the whole thing runs in time which is polynomial in size of G. Okay, and so we need to now show that this works. So I hope we are all convinced that this whole thing runs in polynomial time if 3VC runs in polynomial time. Now we need to convince ourselves that if this says yes, then answer there is yes. If it says no, then the answer is no. Okay. Now, supposing G has a vertex cover of size k. Okay, so let's prove both ways. Okay, supposing G has a vertex cover of size k, so G has a VC of size k. So this implies that GL has a VC of size less than equal to k plus L, right? So this has a vertex cover of size at most k plus L, so it will say yes. So this answer will be yes. Okay. Okay. So this is fine. What we need to do is also the other way around, that if it does not have a vertex cover of size k, then GL will answer no. Okay, so maybe it's better to just do it the other way around. So if this says yes, if 3VC says yes, okay, this means that GL okay, so 3VC says yes, this means okay, GL has a vertex cover of size k plus L, and we know that this implies that G has a vertex cover of size at most k, right? So G has a size of vertex cover at most k, so this is also fine, so which means G has a vertex cover of size k. So both ways we have proved that the algorithm works. So if it has a vertex cover of size k, well, here it's actually k plus L. Okay, G has a vertex cover of size k, this implies that GL has a vertex cover of size k plus N, and we are done. Okay, which means if G has a vertex cover of size k, then it answers yes, and if it answers yes, then G must have a vertex cover of size k. Okay, okay, so this proves that 3VC is NP complete. Okay, our next problem is it's called exact cover. Okay, so it's called exact cover, and it goes by XC, exact cover. Okay, here the input is a set S, okay, and a collection of subsets of S, okay, A1, A2, and so on up to AM. So there are M subsets of S. The question we ask is the following: is there a subcollection of these sets? Okay, so that the union is S, and the sets in this subcollection are disjoint. Okay, so is there a subcollection okay, so let's say AI1, AI2, so on up to AIT, says that two things, the union must be S, so union or all J, Aij is S. Second thing is that Aij intersect Aik is null set. Okay, so you need to pick some of these subsets in this collection so that each element is present in one of them and exactly one of them. Okay, so each element is covered and it's covered exactly once. So that's where you get the name exact cover. Okay, is there a sub collection which exactly covers the set S, which covers the set S in the sense that the union is S. Okay, the union of Aij is S, and it's covered exactly in the sense that each element is covered exactly once. So these must be disjoint. Okay, so is this problem NP complete? The answer is yes, as you must have guessed, because those are the problems we are discussing. So let's prove that this problem exact cover is indeed NP complete. Okay. So the first thing to note, first thing to prove, is to prove that exact cover is in NP. Okay. To prove that this is in NP, so what is a yes input? A yes input is just collection of I need a collection so that there is some sub collection. Okay, so that the union is S and the sets in the sub collection are disjoint. Okay, so I guess it must be clear what proof the prover should supply the verifier, so that the verifier can verify that there exists such a sub collection. Okay, in fact the prover just gives such a sub collection. Okay, so the prover tells the verifier what are the sets in this sub collection. The verifier takes these sets, he verifies that they are disjoint, and he also verifies that the union is S, which means every element of S does appear in one of these sets in the sub collection. Okay, so this proves that this problem is in NP. The way we'll prove it's NP hard is to show that if there is a polynomial time algorithm for exact cover, there should be a polynomial time algorithm for less than equal to 3 VC, okay, for vertex cover. Okay, so let's do this. So given a polynomial time for XC, I want to construct one for less than equal to 3 VC. Okay, this is our goal. Okay, so how do we do this? So we want to construct one for less than equal to 3 VC. So I guess the algorithm will take a graph as input. Okay, there is also this K. Okay, we know that delta of G is at most 3. And we want to somehow figure out whether this graph has a vertex cover of size K or not. Okay, so that's the problem we really want to solve. And what we can use as a subroutine is this problem XC. Okay, so somehow we need to use a subroutine for XC to solve this problem on graphs. Okay, so let's just write down what the solutions to XC and solution to vertex cover look like. Okay, yeah, the input to XC is set S and A1 through AM. Okay, this is the input. This is input to VC. Okay, now here what I want to know is vertices to cover all edges. Okay, here I want sets to cover all elements. Okay, by sets I mean sets from this collection A1 through AM, right. So somehow vertices must be there must be some relationship between vertices, okay, and these subsets. So let me say subsets. Okay, there must be some correspondence here, and edges must correspond to elements of S. Okay, if there is such a correspondence, then it looks like there is some similarity between these two problems. Okay, this is what we would like to exploit. So let's do our first sort of attempt at this problem. So we know that the elements of S are edges. So let's just do the blind thing. So we take G. Okay, G is input. Okay, so now I look at G, and I need to convert this input to an input for exact cover. So I say that set S is nothing but the H set of G, and now the subsets must correspond to vertices. Okay, so each subset here must correspond to a vertex in G. And what's the natural sort of correspondence for vertex I add a set AI. Okay, for vertex I, this is nothing but the edges incident on vertex I. Okay, if I take AI to be the edges incident on vertex I, now I have this correspondence, right? So I have the graph G here, and I have S A1 through AM. Picking vertices to cover edges corresponds to picking subsets which cover elements of S, right? Elements of S are edges, so I am covering edges, and each subset is like picking a vertex in G. Picking a subset here is like picking a vertex in G. Okay. Now there is a small problem. Okay. The first problem is I need to pick. There is this K floating here. So I should somehow make sure that only K vertices are picked. Okay, we need this. If I just do this, there is no sort of, I could pick as many of them as I want, right? So a vertex could be, I could pick as many of these subsets. So this fact that in the original problem, I should only be allowed to pick K vertices does not reflect in this transformation. So how do we fix this problem? This problem is easily fixed actually. So what we do is this. So we take K extra elements. Okay. So take K extra elements. We need to, what we are shooting for is pick only K subsets. This is what we want to do. Okay. So S now, apart from EG, there will be some K extra elements, let's say x1, x2, so on up to xk. Okay. And supposing the sets were A1 through AN, what I do is I take the following, I change the collection of sets. So I take A1 union x1, A1 union, sorry, this is x1, x2, and so on, A1 union xk. Similarly, A2 union x1, and so on up to A2 union xk. And finally, AN union x1, so on up to AN union xk. Well, n is the number of vertices in the graph. That's why it's n here and not m. Okay, n is the number of vertices. Okay. Well, the number of the collection has now grown by a factor of k. Initially you had n sets and now you have k times n sets, right? But now let's see, supposing I pick an exact cover here, okay? Supposing I pick an exact cover from this collection, from these I can pick any one of them, right? But if I look across across a row here, I can pick only one of them, right? So from this I can pick only one, from this I can pick only one, and so on, and from this I can only pick one, right? So totally I can pick only k sets. Okay, so let me sort of say this argument again. Now when I look at this collection, then in each set one of x1, x2, x3 up to xk occurs. Okay, in each set one of these k elements must occur, right? And if x1 occurs, I mean it occurs in many sets, I can only pick one of them because x1 has to be covered exactly once, right? In fact, I pick exactly one of these sets. So I have to pick a set which contains x1, I have to pick a set which contains x2, I have to pick a set which contains x3, and so on up to xk. These are k sets, and I cannot pick any more because any other set has to contain one of these elements x1, x2 up to xk. Okay, so this trick forces you to pick, when you pick an exact cover, this trick forces you to pick exactly k of these sets. Okay, so that's taken care of. So is there any other problem? Well, unfortunately there is. The problem is that in vertex cover, so let me sort of tell you what the problem is. So the problem is this. So when I look at a graph, okay, I look at a vertex cover, you know, it may so happen that there may be an edge between two vertices in the vertex cover. So this is the vertex cover. Okay, it may so happen that there is an edge between two things in a vertex cover. So when I pick the corresponding sets, okay, ai1 and so on, this is ai k. When I pick the corresponding sets, then you know this edge gets covered twice. Okay, it gets covered when I pick this vertex, I mean this set, it also gets covered when I pick this set. So this is a problem. So what we would like to do is when you get to this vertex, not pick this edge, but maybe pick the other edges which have not yet been covered. So I would like to pick these sets one by one, but when I get to a vertex, I would like to pick those sets, those edges which have not been covered. Okay, and the solution is actually simple. So supposing I had recall that the degree of each vertex is 3. Okay, supposing I had a vertex of degree 3. Right. So there are 3 edges which are adjacent. Let's say E, F, and G. Now it could so happen that by the time I get to this vertex, and I would like to pick this vertex, these edges, some of these edges have already been covered by other vertices. Then I would like to only pick G. Let's say if E and F are already covered, I would like to only pick G for this vertex. If only E is covered, I would like to pick only F and G. And similarly, if none of them are covered, then I would like to, you know, have a set which contains all of them. Okay. So the trick is to just take all possible subsets. So take all possible subsets. Okay. So initially I had with a vertex I had the set E, F, G. Now I'll have many of them. Instead of this, I'll have now E, F, G, and then all pairs E, F, and so on. Okay, and finally E, F, G. So there are 7 of these. With each vertex. Okay. Well, actually, this would have x1, x2, and so on up to xk also. So that also has to be put in. Okay. So this set would have E, F, G, and one of the xi's. Remember our previous construction? Okay. So that xi would also go into each of them. Okay. So it's not 7 subsets, but it's 7k times. It's 7k. Okay. With each vertex, I had k such sets, one for x1, one for x2, and so on. Okay. Now I have 7k subsets per vertex. Okay, I have 7k subsets per vertex. If the vertex had degree 2, okay, then it would be less. Okay, then it would be 3k. Okay, because there are, if I take a set of size 2, the number of distinct subsets which are not empty is 3. Okay, and if the vertex had degree 1, then I would just have one subset which would translate to k subsets. Okay, so when the vertex has degree degree 3, I have 7k subsets per vertex. So this is the translation. I take this graph G, and for every vertex, U, okay, so I must say that the set S is nothing but E of G union x1 through xk. Okay, for a vertex U, I would have either 7k or 3k or k sets depending on the degree of a vertex. Okay, so and what does a typical set look like? So it's a subset of edges adjacent to incident on U and one of the xi's. Okay, so I take a subset, an x1 subset, an x2 subset, an x3, and so on up to xk. Okay, so this is how each element corresponding to a vertex looks like. There could be it's either 7k or 3k or k, depending on the degree of the vertex. Okay, and this is now, I take this instance of S and this collection, and I feed this into a subroutine for xc. If this says yes, then I output yes. If this says no, then I output no. Okay, so this is my transformation. Okay, now to see that this works, clearly if this has a vertex cover of size k, I have an exact cover of of this. Okay, why is that true? So let the vertex cover consist of vertices, okay, v1, v2, and so on up to vk. Now for v1, I put the set x1 comma all edges incident on v1. Okay, I pick this set. With vi, I pick the set xi comma all edges incident on vi, but not on v1 and so on up to vi minus 1. Okay, this is my set which I pick, and you can check that this is an exact cover. X1 is covered by this set, the set corresponding to v1. Xi is covered by the set corresponding to vi, and so on. So x1 through xk is covered, and every edge is also covered. Since this is a vertex cover, if I take any edge, it must occur between, there must be one endpoint. Okay, in this there must be at least one endpoint. choose the smaller endpoint. Okay, supposing it is Vi, then this edge must have the other endpoint is either one of Vi plus 1 through Vk or something else completely different. Okay, in either case, that edge will be part of this set. So every edge is covered by this collection. Okay, edge is covered here, so every element of S is covered by this collection. Similarly, if I have a collection which covers okay, let's say B1 through Bk is a sub collection which covers every element of S. Let's say that Bi contains Xi. X1 through Xk must be covered. Okay, so and they are covered exactly once. So they occur there. I must be K sets, and each of them must contain one of X1 through Xk. Let's say B1 contains X1 and so on. Bi contains Xi. Bk contains Xk. Okay. Now every edge, okay, must also be covered and must occur in one of these sets, right? Which means if it occurs in set Bi, it must be adjacent to the vertex I, right? So what I do is the vertex cover just consists of the vertices which correspond to each of these sets. There must be a vertex which corresponds to B1, a vertex which corresponds to Bi, and so on. So those vertices will form a vertex cover. Okay. Okay. So this shows that exact cover is NP complete. Why did we pick 3 VC? Why not, I mean, less than equal to 3 VC? Why not vertex cover? Could we have done this with vertex cover? Well, the answer is no. At least this reduction doesn't work. The reason is that supposing I have a vertex of large degree, okay, some degree d, the number of subsets I have corresponding to this is 2 to the d minus 1 times k. Okay, this is the number of subsets. Okay, remember how we got the subsets for a vertex. We took all possible subsets here, okay, non-empty subsets, and we added, for each such subset, I added x1, x2, x3, and so on up to xk. Okay, so these many non-empty subsets times k, okay, is the total number of subsets we get, and this can be just very large, right? If I have a graph with degree, I mean, for instance, the complete graph has degree n minus 1. Okay, this size can be 2 to the n minus 1, which is just too much. Okay, which is too much, and by the time you write this down, no, it's much more than polynomial time. Okay, so it will not work in polynomial time if you take just vertex cover. So we want this degree to be bounded by a constant. So if you use 3 VC, then this is just 7 times k, which is not too big. Okay, so the total number of subsets we have is actually 7k times the number of vertices. This is the total number of subsets, is at most this much if it's if the degree is bounded by 3. Okay, that's the reason we needed less than equal to 3 VC. So we have shown that exact cover is NP complete. The main trick was to first show that 3 VC is NP complete, less than equal to 3 VC is NP complete, which is a restriction of vertex cover, and then show that exact cover is NP complete. One can actually do it in other ways without going through 3 VC, and I'll let you try this out on your own. Okay, the reductions become slightly more involved, but you can still do them. Okay. After this, we'll look at problems where sizes come into play. Okay, so that's the next installment.